Welcome to Chapter 4, Work, Power, and Energy. The objectives for this chapter are to define mechanical work, distinguish the difference between positive and negative work, define energy, define kinetic energy, define gravitational potential energy, define strain energy, explain the relationship between mechanical energy and work, and define power. In mechanics, work is the product of force and the amount of displacement in the direction of that force. It is the means by which energy is transferred from one object or system to another. Because work is the product of force and displacement, the units for work are units of force times units of length. These may be foot-pounds or Newton meters. In the International System of Units, the joule is the unit of measurement for work. Work and impulse often go hand in hand. We see that when a resistance is moved over a certain distance, not only was an impulse applied to move the resistance, but work was done because displacement does not equal zero. Another example of this is when an athlete applies a force to a javelin for a certain amount of time over a particular distance. So the formula for determining work is then U equals F times D, so force times displacement. To determine the amount of work done on an object, we need to know three things. First, the average force exerted on the object. Second, the direction of this force. And third, the displacement of the object along the line of action of the force during the time the force acts on the object. Let's look at an example. A discus thrower exerts an average force of 1,000 newtons against the discus while the discus moves through the displacement of 0.6 meters in the direction of his force. How much work did the discus thrower do on the discus? Let's go back now to the formula to determine work, where work is equal to force times displacement. If we plug these values in, we get force, we get that work is equal to 600 joules, so 600 newton meters or 600 joules. Therefore, the discus thrower did 600 joules of work on the discus. Let's try another example. A weightlifter bench presses a 1,000 Newton barbell. He begins the lift with arms extended and the barbell 75 centimeters above his chest. The lifter then lowers the barbell and stops when it is 5 centimeters above his chest. He pauses there and then lifts the barbell upward from his chest and back to the original starting position 75 centimeters above his chest. How much work did the lifter do on the barbell from start until the finish of the lift? What was the displacement of the barbell? The starting and ending positions of the barbell were the same, so the displacement was zero. If the displacement was zero, the work done is also zero. This doesn't seem right since we know that the lifter really did expend energy to complete the press. And if it's true that physiologically the lifter did some work, but mechanically no work was done on the bar because it was in the same position when the lift ended as it was when it started. How about we break it down? Was any work done during the raising of the bar? Let's determine the displacement of the barbell during its raising. So D is equal to final position minus initial position. So D is equal to 75 centimeters minus 5 centimeters. So that means 70 centimeters upwards. If we convert 70 centimeters to meters, that would be 0.7 meters for displacement. So returning to our work formula, we could multiply 1,000 newtons by 0.70 meters to get 700 newton meters or 700 joules. If we were to determine the amount of work done on the barbell while lowering it, we would see that the same force and displacement values. However, since the work was done in a downward direction, we would need to assign it a negative value. So if we were to then add the positive 700 joules for the upward work and the negative 700 joules for the downward work, that would lead us to 0 joules of work. Work can be positive or negative. Positive work is done by a force acting on an object if the object is displaced in the same direction as force. Negative work is done by a force acting on an object when the object is displaced in the direction opposite the force acting on it. Muscles also do mechanical work. So when a muscle contracts, it pulls on its points of attachment. Positive work is done by a muscle when it contracts and its points of attachment move in the direction of the muscle force pulling on them. The force, muscle force, and the displacement, which would be the displacement at the point of the muscle attachment, are in the same direction, so positive work was done. Negative work is done by a muscle when it contracts and its points of attachment move in the opposite direction of the muscle force pulling on them. The force, the muscle force, and the displacement, which would be the displacement at the end of the muscle attachment, are in opposite directions. Thus, negative work is done. Keep in mind, not all muscle contractions produce mechanical work. So if a muscle contracts and its points of attachment do not move relative to each other, the displacement is zero. And this happens when we see or when you are doing isometric contraction exercises, for example, a plank. Energy is defined as the capacity to do work. So there are many forms of energy: heat, light, sound, chemical. But in mechanics, we are primarily concerned with two forms: kinetic and potential energy. Kinetic energy is the energy due to motion, whereas potential energy is energy due to its position. A moving object has the capacity to do work to its motion. The capacity is the kinetic energy of the object. But how is kinetic energy quantified? What affects it? The formula for kinetic energy is equal to 1/2 times mass times velocity squared. Thus, the kinetic energy of the object is affected by the mass and velocity of the object. The units for kinetic energy are mass times velocity squared, but this is also equivalent to Newton meters, which is also equivalent to a joule. You can take a look at this example. How much kinetic energy does a baseball thrown at 80 miles per hour or 35.8 meters per second have? If the baseball's mass is 0.145 kilograms, we can use the kinetic energy formula to determine that the amount of kinetic energy that it had is 92.9 joules. Potential energy is the energy or the capacity to do work that an object has due to its position. There are two types of potential energy: gravitational potential energy, which we often refer to as GPE, and strain energy. GPE is potential energy due to an object's position relative to Earth. The gravitational potential energy of an object is related to the object's weight and its elevation or height above the ground or some other reference. Mathematically, the equation for GPE is potential energy is equal to mass times the acceleration of gravity times height. So let's determine how much GPE a 700 Newton ski jumper has when taking off from a 90-meter jump. If we use the GPE formula, we see that they've actually already provided us the mass times acceleration of gravity. So we were able to get our 700 newtons, and we multiply that by the height, which they told us was taking off from 90 meters. So that would give us 63,000 newton meters or 63,000 joules. Another type of potential energy is strain energy, which is energy due to the deformation of an object. The strain energy of an object is related to its stiffness, its material properties, and its deformation. Mathematically, the strain energy of a material with a linear stress-strain relationship is defined as strain energy is equal to 1/2 K times the change in X squared, where K is equal to stiffness or spring constant of a material, and the change in X is equal to the change or length or deformation of an object from its undeformed position. Looking at an example, how much strain energy is stored in a tendon that is stretched 5 millimeters if the stiffness of the tendon is 10,000 newton meters? Using our formula, we see that strain energy is equal to approximately 0.125 joules. In human movement, energy is possessed by athletes and objects due to their motion, their position above ground, that would be their GPE, and their deformation, which would be their strain energy. It's important to mention the stress-strain relationship here. The graph is representative of the stress value of a material on the y-axis and the strain value of a material on the x-axis. If we consider the relationship or the example of bone, when jumping up and down, the longitudinal axis of the femur is subject to stress. So stress is really force divided by cross-sectional area of the material. In this case, that would be the cross-sectional area of the bone and everything that makes up the bone. Now, when a force is applied to this bone from the side, for instance, if somebody runs into you while you're playing soccer, the medial side of the bone is now under tensile stress, while the lateral side of the bone, or the side that you were hit on, is under compressive tension. Since bones are not nearly as strong under tension as they are under compression, this is why bones break or experience stress fractures. The amount of deformation a material undergoes or can withstand is referred to as strain. So when the lateral force was applied to the femur, the medial side was experiencing strain. The material was essentially being stretched or elongated, and a bone can only handle so much strain before it fractures. The slope of the stress-strain curve above is referred to as Young's modulus. During this stage, the material only undergoes elastic strain, meaning it can return to its original shape. The initiation point of plastic deformation is referred to as yield strength. This is where we start seeing more long-term changes to the material occur. Strain hardening and necking that you see up top with ultimate strength, that's really where the material is experiencing the maximum amount of strain that it can handle. Essentially, the cross-sectional area of the material under strain becomes significantly smaller. If a force continues to be applied, the material will break or reach the fracturing point. In sports and human movement, we are often concerned with changing the velocity of an object. Changing velocity means changing kinetic energy, and the work energy principle shows how kinetic energy can be changed by doing work. More often, work is done and thus a greater change in energy occurs if the average force exerted is large or the displacement in line with this force is long. Using the impulse-momentum relationship as the basis for technique analysis, the creation of a large change in velocity requires that a large force be applied over a long time. The work energy principle indicates that the production of a large change in kinetic energy, and thus a large change in velocity, requires application of a large force over a long distance. The work energy principle can also be used to explain the techniques used in transferring or absorbing energy from an object. We see this when we catch a ball, for example. This would be negative work. When you catch a ball, its kinetic energy is reduced or absorbed by the negative work you do on it. The average force you must exert to absorb the energy or absorb energy in catching a ball or landing from a jump depends on how much energy must be absorbed and over how long a distance you can apply the force. These actions increase the distance over which the force acts, thus decreasing the average value of the force. Early in the 20th century, shot putters began their put from the rear of the ring. The initial stance was similar to that shown in the photo on the left, and early on, the athlete's shoulders were turned slightly to the side in which they were dominant. So right-handed thrower's shoulders were turned slightly to the right, and the shot putter would then hop across the ring on his right leg and put the shot. Gradually, the technique evolved and the putter's shoulders were turned more and more toward the rear of the circle in the initial stance. It wasn't really until the 1950s when shot putters began putting the shot from an initial position in the rear of the ring facing the opposite direction of the put. And what this allowed for was the putters to really maximize the displacement of the shot in the direction of force application. It allowed them to apply a greater impulse, which then allowed them to transfer a larger amount of kinetic energy. The work-energy relationship is also useful when we examine situations in which no external forces act other than gravity. In these situations, no work can be done because no external forces act. If no work can be done, the total mechanical energy of the object in question is conserved. Gravity is the only external force that acts on a projectile. If this is true, the total mechanical energy of a projectile does not change during its flight. Consider dropping a ball. Just before you let go of it, the ball has potential energy due to its position, so that would be gravitational potential energy, but no kinetic energy because it's not moving. During flight, the gravitational potential energy decreases while the kinetic energy increases as it accelerates downward by gravity. This increase in kinetic energy is exactly matched by the decrease in potential energy, so the total mechanical energy of the ball really does remain the same. The ability of an athlete to increase the displacement of an object or body while exerting a force affects performance in many skills. In some sports, excelling requires not just the ability to do a large amount of work, but also the ability to do that work in a short amount of time. Power is the mechanical term that describes this ability. Power is the rate of doing work, or how much work is done in a specific amount of time. This concept is useful in biomechanics for several reasons. If you consider the power clean, it is nearly impossible to do this lift slowly. If you compare it to the deadlift, though, while you would be able to lift more weight with the deadlift than the power clean, their speeds or time rate in which they are completed are totally different. Often the deadlift is slower, meaning that as the amount of force required increases, the velocity of which the movement can be done decreases. This is also same for the opposite side of the spectrum. As the amount of force needed decreases, the rate at which the movement can be performed increases. And this really does lead us to what's called the force velocity curve, where we have any absolute output of force is going to result in very low values of velocity, meaning if you do a maximal force application, you're probably not going to be able to do it moving quickly, and vice versa, right? The lesser amount of force application, the quicker you might be able to move the implement or an appendage, for example. All right, that wraps up chapter 4. Pretty short and sweet.